Hello everyone. In this video we are going to consider the basic concepts of machine learning. Specifically, we are going to look at the difference between artificial intelligence, machine learning and deep learning, and then we'll consider the difference between machine learning and classical programming, and after that we'll look at what learning means, and then we'll consider the three common types of learnings, which are called supervised, unsupervised, and reinforcement learning. So to start with that of artificial intelligence. Artificial intelligence is the engineering of making intelligent machines and programs with certain cognitive functions. And here, when you say cognitive functions, it is the development of intelligent machines, or specifically computers, with the ability to perceive, think, learn, reason, remember, and also make decisions like that of a human does. And under artificial intelligence, there is a component called machine learning. It is the development of algorithms to learn patterns from a certain available data without being explicitly programmed. So here the learning could be in terms of input-output relationships, data distributions, or even it could be through an interaction within a certain dynamic environment. And under machine learning, there is another subcomponent called deep learning. And like that of machine learning, it's a method of learning based on neural networks having several multiple layers. So deep learning can learn patterns almost from any form of data, including text, image, video, audio, and so on. Now let's consider the difference between machine learning from that of the classical programming technique. In the classical programming technique, we have inputs and rules. These inputs and rules are provided as an input to the system, and the system is expected to provide the outputs. So here the rules are needed to be explicitly coded by the developer. For example, if we want to determine whether a number x is even or odd, what we are going to do is we need to divide the number by 2 and then get the remainder, and after that check whether the remainder is 0 or not. So if the remainder is 0, the number is even, otherwise it's not. So the rule here is x modulus 2, or the rule here is getting dividing the number by 2 and getting the remainder, and after that setting, or let's say checking whether the remainder is 0 or not. So this rule, that is just dividing the number by 2 and then checking whether the remainder is 0 or not, should be hard-coded by the developer. So this type of programming is actually a deterministic type of programming. When you come to that of machine learning, the inputs and the outputs are provided as an input, and then the system is expected to figure out the rules that associate the inputs with the outputs. So here, unlike that of the classical programming, the system learns the rules or the model by itself. So for the previous example, to determine whether a number is even or odd, instead of giving a certain fixed rule, what we are going to provide is examples or data, the inputs and the outputs. So the inputs could be, for example, 2, 4, 1, 3, and the outputs could be their corresponding labels, even, odd, odd. Then here we do not tell what an even or an odd means. Rather, the system will figure out the rules from the provided data by itself. So unlike that of the classical or traditional programming, machine learning techniques are probabilistic. Now let's define what learning means. Now learning is finding empirical data-driven solutions for problems with unknown or complex relationships when no analytical solutions exist or when mathematical formulations are interactive. So in this definition, there are three key aspects of learning. One, there is a problem governed by unknown or highly complex rules, and the problem cannot be also expressed analytically or using a certain closed form solutions or explicit formulas. And then to drive solutions for the problem, there should be a large amount of data from which the patterns can be learned. Now let's consider the different types of learning. Based on the type of feedback or learning signal, there are three common types of learnings. One, supervised learning, and the other, unsupervised learning, and the third one is reinforcement learning. In the supervised learning, we have data is to be provided, including the labels, or here when I say labels, it is to mean just the dependent variable or the outcome variable. So the interest in supervised learning is to map the inputs with the outputs, or to map the inputs with the labels, so that the error is going to be minimized. In the case of unsupervised learning, we have data, but there is no specific outcome or dependent variable. So the interest is to group the observations into different classes, or to group the variables into different, say, components. And in the case of reinforcement learning, an agent is going to interact within a certain dynamic environment. And by interacting within a certain dynamic environment, that agent will get certain reward, or let's say penalty. Then the objective here is to maximize the total cumulative reward of the agent, so as to determine the optimal action that should be taken within that dynamic environment. So see in more detail, let's start from that of the supervised learning. So in the supervised learning, the objective is to approximate an unknown function f that maps from the input space x to the output space y. That is, we are interested in approximating or estimating the model y equals f of x plus the error term e, given that a certain finite set of input-output pairs dataset D. So here the dataset D has inputs, usually denoted by capital X, consisting of all possible covariates, and we have an output, or which we call label Y. Then once we have these input features and the label or the output feature Y, the objective is to find a mapping from the input space to the output space Y. So here the term supervised refers to the fact that the target values or the dependent variable or the outcome variable provides a supervisory role. And specifically in the statistical models, we have what called generalized linear models, which consist of linear regression, logistic regression, Poisson regression, or those parametric survival regression models and others. So all those generalized linear models can be considered as supervised learning type of machine learning techniques, because there is an outcome variable that's going to be predicted or determined. So in such models, or in such generalized linear models, there are three main components. One, we have a random component, which specifies the probability distribution of the response variable or the outcome variable. And the second component is the systematic component, which is the deterministic part. And this systematic component or deterministic part is often expressed as a linear function of the covariates, and particularly it is usually called as linear predictor, which may be expressed as z equals b plus w1 x1 plus w2 x2 plus wp xp. So this linear combination is the linear predictor or the systematic component of any generalized linear model. So here b is nothing but a bias in machine learning, but in the statistical terms it is called an intercept, and the wi's w1, w2, wp are the coefficients associated with that of the covariates. So in machine learning these wi's are called weights, but in statistical terms they are called parameter estimates, or they are called coefficients. Then we need to have the third component, which is called link function, that connects the random component with that of the systematic component. So for example, for linear regression, the distribution of the response variable is Gaussian, so the random part is the mean response. And here the link function is an identity link function. If we find the inverse of that link function, just the inverse of an identity link function is just the identity link function it is. So in linear regression, the mean response is directly equated with that of the linear predictor without any transformation, because it uses an identity link function. In the logistic regression model, specifically in binary logistic regression model, the distribution is binomial, and the random component is the probability of success, or the probability of one of the outcome in which we are interested in. So here this probability is going to be equated with that of the linear predictor. For this purpose we need to have the log odds link function or the logit link function. And the inverse of this log odds or logit link function is called sigmoid, which is just 1 over 1 plus e to the power of minus z. Now for any value of the linear predictor, this sigmoid function will return values in between 0 up to 1. And for a Poisson regression model, we have a Poisson distribution, and we are interested in modeling the mean response, and the link function is log link. Then the inverse of the link function is an exponential function. So for this exponential function, just for any value of the linear predictor z, the exponential function e to the power of z will provide values greater than or equals to 0. And the same is true for that of parametric survival models, like that of Weibull regression model. Now in supervised learning there are two basic tasks. One is a regression problem, and the other a classification problem. So in the regression problem we are interested in predicting a continuous, or in general a quantitative outcome variable. So the objective is to estimate a model of the form y hat equals b plus w1 x1 plus w2 x2 plus wp xp. So this linear regression or line of regression is going to be estimated. So as an example, we can consider estimating tumor size and predicting HIV viral load over time, and so on. In the case of classification problem, we are interested in predicting a certain categorical outcome variable, which could be binary, multinomial, or ordinal. So like that of estimating a regression line for a regression problem, here in the classification problem we are interested in determining a decision boundary. This decision boundary is nothing but the linear predictor equals to 0. So if the linear predictor has a value 0 or greater than 0, it predicts, let's say, class 1, but if it is less than 0, it predicts, let's say, class 2. So as an example, for example, you can consider patient outcome, days or not, TB detection from radiological images, positive or negative. So let's consider the plots on the left hand side of a regression problem, where the input x is labeled along the x-axis and the output y is labeled along the y-axis. So here the objective is to estimate the regression line that best fits the points. But in the case of a classification problem, let's say for a binary classification problem, let class 1 represents the red points and class 2 represents that of the green points. Then the objective is to classify or discriminate these red points from that of the green points. So the line that separates these two classes is said to be decision boundary. So here specifically here in the regression and also in the classification problems, we have just linear models. But in practice or in reality, the model of interest could be nonlinear. There could be a nonlinear regression model or there could be a nonlinear classification problem. So now let's consider that of the linear regression. In the linear regression, the identity function is a link function. So y hats can be expressed as b plus w1 x1 plus w2 x2 plus wp xp. So here, for example, we can consider p plus 1 inputs, including that of the intercept, and the output is z. So we have p plus 1 inputs and we have one output z. Therefore, this type of representation is called single layer neural network. So simply we can consider linear regression as a single layer neural network model. So when you consider that of logistic regression, it's almost the same, but here the linear predictor should pass through that of a sigmoid function, so that the output becomes in between 0 and 1. So the difference here is only just on the output layer. We have a sigmoid function, sigma of z. Therefore, the linear predictor or linear combination of the covariates is passed through that sigmoid function, and the output provides a value somewhere in between 0 and 1 inclusive. And the other is the unsupervised learning. Now, in the unsupervised learning, there is no specific outcome variable to be considered. So here, the objective is to identify hidden patterns, structures, or groupings among the observations or the variables in a certain particular dataset D. So here, when you say data, we have two components. One, we have observations along the rows, and the other, we have variables along the columns. So the grouping could be among the observations, or the grouping could be among the variables. So for example, if we consider the left hand side picture, initially we have a three-dimensional data. Then this three-dimensional data is transformed into a two-dimensional data. Therefore, we go from 3 variables to a 2 variables data, or let's say model. So such kind of grouping is called unsupervised learning. Specifically, such way of just reducing variables into a few components is called dimensionality reduction. In the second plot, that's of the right side plot, along the x-axis if we consider as x1, along the y-axis if we consider as x2. Now clearly there are 2 types of clusters. So let's say the first cluster, that is the one that is shaded like which is colored like a blue, and let's consider the second cluster as something like shaded by red color. So here initially we have a number of observations, but this number of observations are grouped into 2 clusters. So in the unsupervised learning, basically, one, we have clustering, which is just segmenting observations into similar groups. For example, it could be grouping patients based on laboratory results, vital symptoms, demographics in order to discover certain clinical subgroups. So here, there is no specific outcome variable, but just the patients are grouped based on their characteristics. And another, we can consider dimensionality reduction, which is just there could be a large number of features to be included in a particular model, let's say. Then the objective is to reduce this large number of features into a few components, preserving the important structure or variability of the original dataset. There, for example, in gene expression analysis, there could be thousands of features. So the objective could be to reduce or convert these thousands of features into a few informative components. And another type of supervised learning could be anomaly detection or outlier detection, which is used to identify rare or unusual observations. So here, for example, the objective could be to identify unexpected adverse reactions to a certain drug, or it could be to identify or detect abnormal spikes or drops in a certain health-related biomarker. And another type of unsupervised learning could be association rule mining, which is used to discover rules or patterns between variables. This is often used in market basket analysis. For example, an individual who orders macchiato may be more likely to order muffin, or an individual who orders muffin may be more likely to order macchiato. So such kind of relationship is called association rule mining. Specific to, let's say, health-related studies, this could be applied for comorbidity patterns or for studying, let's say, communication rules. And the third type of learning is reinforcement learning. Now, in reinforcement learning, an agent learns through trial and error based on a sequence of interactions within a certain dynamic environment. So, in a particular environment, the environment may be in state ST, then the agent takes an action AT. After that, the agent will receive a reward RT for taking that action AT. And then the agent moves to the next state ST plus 1. So the aim here is to learn a policy that maps the states to the actions in order to maximize its expected cumulative reward. So for example, in state ST, the agent could be the agent could select an action AT. Then after selecting an action AT, that agent will receive a reward RT. Then after receiving that reward RT for taking the action AT, the agent will move to the next state ST plus 1. Then again in state ST plus 1, that agent will select an action AT plus 1. And then the agent will receive again a reward RT plus 1. And then the process continues for all time steps with the objective of maximizing its cumulative reward. The way that the data is going to be structured in reinforcement learning is something like this. At time step 1, the environment may be in state S1, then the agent will select the action A1, and then it will the agent will receive a reward R1, and after that the agent moves to the next state S2 at time step 2, and again the agent will select the action A2 and then receive a reward R2, and after that it moves to the next state S3 at time step, let's say 3. Then this sequence of interactions with the dynamic environment will continue for all time steps, and the final goal is to learn a policy pi that maps the states with the actions so that it maximizes its expected cumulative reward. Now let's consider these three simple examples and identify whether Each example is supervised, unsupervised, or reinforcement learning. Recommending a medical book to a user in an online bookstore. Here, it can be considered as that of a supervised type of learning. The user preferences, the label or the dependent variable, and the characteristics of the medical box can be considered as input features. Categorizing movies into different types. Now for this case, if the labels are given like that of romance, action, and so on, categorizing movies into different types could be considered as supervised type of learning. But if the labels are not given, and if we are interested simply in categorizing the movies into different types, in that case, this could be considered as unsupervised learning. And third, let's consider learning how to play music. Now here, if we learn the music by ourselves, it is unsupervised learning. If we learn the music by a teacher, or let's say an instructor, it is considered as supervised learning. If we learn the music by ourselves, but if another person judges whether our music is good or bad, in that case, learning how to play music can be considered as a reinforcement type of learning. So here are these solutions for you to pause and look at. So this is all about today's video. Thank you.